Your feed service containers are OOM-Killed every 30 minutes during peak hours. Each request loads the entire user graph into memory, 6 GB per container despite a 4 GB limit. Here's exactly why and how to fix it. Let's start with the basics. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Design Instagram. Instagram is a massive photo album shared by the world. When you upload a photo, it goes to object storage, then copies are made for your friends' feeds. The tricky part? Millions upload every second, and each feed is personalized. You can't show everyone the same photos, you need to sort and rank them just for you fast. Most tutorials start with upload. Client sends photo, server stores it. That's the easy part. The real nightmare is the red path, generating a personalized feed for 500 million users under 500 ms. The core problem is fan-out. When a celebrity with 10 million followers posts, you need to insert that post into 10 million feed caches. Do it synchronously, and your write latency explodes. Here's the hybrid fan-out logic. For users with fewer than 10,000 followers, we push posts to their feed cache on upload. For larger accounts, we pull on read by fetching recent posts from followees. This prevents write amplification from celebrities. User data needs to be sharded across databases. The naive approach is modulo n, but that breaks with hot users. Instagram uses two-level sharding, first by user ID hash, then by logical shards per physical database. This allows resharding without downtime. Always keep a user's posts on the same shard as their profile to avoid joins. This function maps a user ID to a physical database. The logical shard is computed by hash, then a config file maps it to a physical DB. When resharding, update the map gradually and move data in the background. Instagram caches each user's feed as a sorted set of post IDs in Redis, scored by timestamp. On scroll, they read from cache. Cache misses fall back to the pull-based generator. For media, a content delivery network caches at edge locations with a hit ratio above 95%. Never cache full post objects in Redis, store only IDs and metadata. Here we add a post to the feeds of hot users only with a TTL of 1 hour. When reading, we try cache first, then generate on miss. This keeps latency low for active users. When a user uploads a photo, the client sends it directly to a content delivery network upload endpoint, not your server. The content delivery network returns a URL, and your server receives only metadata. This offloads bandwidth. The bottleneck is the database write, so we buffer writes with Kafka and batch them into the database. The upload handler validates metadata and sends it to Kafka, returning a 202 accepted. A consumer batches up to 100 posts before inserting into the database. This prevents connection pool exhaustion. Instagram's feed isn't just chronological. It's ranked by a machine learning model considering affinity, timeliness, and content type. The ranking service must complete in under 100 ms, so it uses a lightweight model with pre-computed features stored in Cassandra. This simplified ranking multiplies affinity by recency. In production, affinity is pre-computed daily and cached, reducing ranking latency from 500 ms to 10 ms. A user with 50 million followers posts a photo. If you push to all synchronously, your feed cache write rate spikes to 50 million writes per second. The solution? Use a pull-based model for users with more than 10K followers. Only push to the top 10K most active followers, the rest fetch on read. This function checks follower count. If below 10K, push to all. If above, push only to active followers and mark the post for pull-based retrieval. This prevents write amplification. Instagram uses PostgreSQL for user metadata and posts, Cassandra for the social graph, follows, and Redis for caching. PostgreSQL provides strong consistency for transactions, Cassandra handles high write throughput for follows, and Redis provides low latency reads. Eventual consistency between systems is acceptable. This architecture is overkill for a photo-sharing app with fewer than 1 million users. For an MVP, use a monolithic backend with a single PostgreSQL database and a content delivery network. Only adopt these patterns when you see specific pain points. Feed latency 1 second, database CPU 80%, or upload failures. This is the same issue we highlighted at the start. Here's exactly why that happened. Each feed generation request loaded the entire user graph, followers, followees, into memory. With 10K concurrent requests, memory spiked to 6 GB per container despite a 4 GB limit. The containers were OOM-Killed every 30 minutes. The fix was to lazy load the user graph with a TTL cache in Redis. Instead of loading everything, we fetch only what's needed and cache it. We also reduced the batch size to 100 users per request and increased container memory to 8 GB with a 6 GB soft limit. This resolved the OOM kills. Never load the full social graph in memory per request. Cache it with a TTL and paginate the fanout. This was the root cause of the production incident. When a celebrity posts, pull-based followers will all try to generate their feed simultaneously. Use a mutex lock per user to prevent multiple requests from regenerating the same feed. Otherwise, your database will be hammered. If you push every post to every follower synchronously, a single post from a celebrity can cause 10 million database writes. Your write throughput will collapse. Always use a sync fanout with a message queue and batch writes to the feed cache. If you store user profiles in PostgreSQL and posts in Cassandra, don't try to join them in application code. You'll end up with n+1 queries. Instead, denormalize. Store a user's recent post IDs in the user profile row. When a user unfollows someone, you must delete that user's posts from the follower's feed cache. If you forget, stale posts appear in feeds indefinitely. Do this asynchronously with a background job. Writing to the database on every upload will cause connection pool exhaustion under load. You'll see error, connection pool exhausted in your logs. Always buffer writes with a queue. Don't compute affinity on the fly. Run a daily batch job that calculates affinity scores for each user-followee pair and stores them in a cache. This reduces ranking latency from 500 ms to 10 ms. The article mentions Unfollow invalidation, but doesn't show code. Here's a concrete implementation using a background job to remove posts from the unfollowed user in the follower's feed cache. The article uses timestamp as the score in Redis sorted sets. In Redis, scores are double precision floats, which can lose precision for timestamps in milliseconds. For high-throughput feeds, use a combination of timestamp and a unique counter to avoid score collisions and ensure correct ordering. The article mentions using a mutex lock to prevent multiple requests from regenerating the same feed. Here's a Redis-based distributed lock implementation for feed generation. To debug feed issues, first check Redis cache hit ratio. If low, look for cache stampede. Check Kafka consumer lag to see if uploads are backing up. Also check DB connection pool with show status like threads connected. For stale feeds, verify unfollow triggers cache invalidation. Let's run through some common interview questions. How does Instagram handle fanout for millions of followers? Hybrid push-pull with 10K threshold. When to choose push versus pull, push for low follower count, pull for high to avoid write spikes. What happens when a celebrity posts? Thundering herd, mitigate with mutex lock and pre-warm cache. And a few frequently asked questions. How does Instagram generate feeds? Hybrid fanout with push-pull and ML ranking. What's the difference between push and pull? Push pre-computes on post, pull computes on read. How to handle celebrity posts? Pull-based with mutex lock and pre-warm cache. To recap, the read path is the real challenge. Use hybrid push-pull fanout with a threshold. Cache only post IDs in Redis, not full objects. And start monolithic, only scale when you see pain points. Ready to go deeper? Up next, design a distributed message queue, then design a distributed key-value store, then design object storage, simple storage service. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.